Okay, so welcome back, and we go on to the next demo session, which will be task switching. So we discussed our task switching in a very broad way in the previous sessions. Now we will have a much more better deep understanding of task switching, and then followed by one code which will demonstrate this task switching in its full perspective. Okay. Now let us see what is a task. Task is nothing but a unit of work performed by processor, which is to primarily to execute a process or serve some operating system utility or handle interrupt or exception. So task can be of three forms. One, it can be an application program executing, or it can be a device driver executing, or some operating system utility that is executing, a scheduler executing, etc., or it can also be an interrupt service routine that is executing. So there are three different types of task by this type of a classification. So everything that is executing in the processor is essentially a process, and that is called a task. So everything that is executable on the processor essentially is a task. Now what is task management and why it is very much important for information security? Now what do you understand by the term task management? How hardware handles multiple tasks and protection among them. This is the most important thing that we need to look at, right. So and we have to look at from two perspectives, namely the task execution perspective and the task switch perspective. When I am executing a task, I have certain privileges, I do not have certain privileges. When I move from one task to another task, I can make the move, I cannot make the move. I can make a move from my task to some task A, but I may not be allowed to move from my task to another task B. So when we talk of task management, the main issue is executing the task is a programmer's problem, but when I execute the task, what are the privileges that I have, what are the privileges I do not have, essentially is a part of task management. And when I complete the task and move out, or during the task I switch to some other task, which are the tasks I am supposed to switch and which I cannot switch, this is also part of the task management. And these two conditions are basically governed by security. Why should I not go to some other task? For security reasons. Why should I not, when I am executing, why should I not access certain routines or access certain objects? That is again due to privilege reasons or security reasons. So security basically dictates task management from these two perspectives. Again repeating that when I am executing the task, what is it I am allowed to access and what I am not allowed to access, and from a task which are the other tasks I could switch on and which I cannot switch on. So if task management is not made protected, then anybody can access anything else, and essentially there is nothing called secure data at all. And so that is the basic threat to the first and probably the largest threat to information security. So this task management forms a hard crux for information security. Now what we will do is how x86 architecture handles this both task execution and task switch is what we will see as a part of this session. Now what is inside a task? A task has an execution space. What do you mean by an execution space? Space means some amount of memory in which I carry out my execution, using which I carry out my execution. So the memory basically has code, it has stack, and it has one or more data segments that is used by the task. So where are these information captured? Like as a task, what is the data segment I can use, what are the stack segment I can use, etc. These are all captured by what you call as the task state segment. In a task state segment, essentially I could say that this is a metadata of task execution space, essentially used to identify the memory location of each segment, right. So, we have already saw the structure of a task state segment, it has 104 bytes, but I am going to go much deeper into that in this session. So, what will the task state segment hold? It will hold all details about the task, and what are those details? One of the most important thing is that it holds the context of the task. What is the context of a task? I explained that in the earlier sessions, but I repeat here, it is the basic minimum information required for me to restart a task after once it gets suspended, okay. And this information is basically stored in the task state segment. Now, this is the basic task structure. There is a task state segment, and in the task state segment you store all the selectors to the code segment, to the data segment, to the stack segment, to the stack segment of the current privilege level, and then you have pointers to stack segments of privilege level 0, 1 and 2, and then you can store your LDT, the local descriptor table, then also you can store what you call as the CR3, which is the start of a page table. As you go into versions of Unix, you will understand that a page table, every task can have its own page table also. So that is also captured in the task state segment. In addition, where will the task state start? Where will the task state segment start? That location is basically pointed to directly or indirectly by a task register, okay. So this is how a task state segment looks like, and the task state segment essentially dictates the structure of the task. So the information essentially has, in addition to the segment selectors, the current segment selectors CS, DS, SS, ES, FS and GS. Please note that in point number 7 in your slide, you have the LDTR. It essentially has a pointer to its current LDT. So all the segments associated with the stack is basically captured through that LDT. It also stores at the time of suspension whatever was were the current values of current selectors that are stored in CS, DS, SS, ES and FS and GS, that also it captures exclusively. In addition, it stores the value of all the general purpose registers EAX, EBX till ESI, EDI, ESP, all the 8 general purpose registers. Sorry, there are only 4, there are totally 8 of them. These are all also stored at the time of suspension, that value is stored. At the time of suspension, whatever is the value of EFLAGS, that is also stored. At the time of suspension, whatever is the value of EIP, extended instruction pointer, that is also stored. Then the physical address of the page directory used by the task, because each can have its own page directory, as I mentioned here, that is also stored there, right. And the task register's value, there is a load for the task register value, you can also store that. And then the stack pointers of PL0, PL1, PL2 stacks, and the selectors of SS0, SS1, SS2, SS3, all these things are SS2, all selectors for these different stacks are also stored. And then there is also a link to previous executors task, which you can use for task switch purposes. So that to sum up the data structures that are needed for task switching, there are 2 ways. I can jump or call directly to a TSS descriptor, right, and immediately there will be a task switch, because the TSS descriptor will point to a task state segment, and in the task state segment there will be a EIP. So whichever task state segment that TSS descriptor points to, I jump to that task. So, that is method 1. Another way is I go through a task gate, and from there task gate I go to the TSS descriptor, and then I go to the task state segment, I get the new address and start executing. So, there are two methods by which I can do task switching. So, the method 1 involves a task register that directly points to a TSS descriptor, and the TSS descriptor is a descriptor for TSS, and that will point to a TSS, and I get the EIP, which is the next instruction to be executed. In the method 2, I go to a task gate descriptor, which is indirected / protector pointer to the TSS descriptor, and from there I go to the TSS descriptor, and from there I go to the task state segment. Okay. So, these two methods do exist, while the second method is introduced to get more security than the first method. And there is one thing called nested task flag, NT flag, in the extended flags register, which actually controls the chaining of interrupted and called tasks. So, one task calls another task, automatically that NT flag becomes 1. When one task essentially gets an interrupt, and by that it goes to the interrupted task, then NT flag is basically set to 1. Why is NT flag set to 1? If I do a jump, it is not set to 1, because there is no way by which I am going to return back. But if I do a call, then I will return back. So, this is why the NT flag basically tells, is there a task switch that will, which it gives out a possibility of going back to the original task at all. If that possibility exists, then your NT flag is set to 1, otherwise your NT flag is set to 0. So, this is something which has been followed by the x86 architecture. So, this is method 1 for task switching. So, there is a task register which stores a selector. That selector points to a DSS descriptor inside the GDT. Please note that TSS descriptors can be stored only in the GDT. Now, this TSS descriptor has a base address and a segment limit. So, the moment I store, when I load LTR with that selector value, the base address and the limit goes into the invisible part. Why I do that? For performance reason. Yesterday we also saw in the segmentation that there is always a hidden part, and the data goes and stays in the hidden part. The limit, base and the privilege level goes and stays there. So, here the base address and limit goes to an invisible part, and based on that, now the TSS, now this is how a TSS is basically defined and stored. So, now the TSS has two components, as I see. That visible is the software controlled part, which is 16-bit segment selector, and what does segment will select? It will select a TSS descriptor, and there is an invisible part which is controlled part, which has 32-bit base, 16-bit limit and descriptor attributes for TSS descriptor, right. So, there are some caching purpose, etc. So, all these things are invisible part, and why I need that invisible part? As a programmer, I do not really care about that invisible part, but why I need that is because for performance reason. Okay. So, if I go and change something in the TSS, I need to go and do again an LTR, load the task register, to see that those things become effective. You got this? So, if I go and change something in the TSS descriptor, I have to do an LTR again, so that hidden part gets updated. So, this is very similar to what we have seen in yesterday's lecture, right. If I go and change a segment descriptor's base address, unless I load that selector again into the corresponding segment register, that change will not be affected, because the base, limit, etc. are stored in the hidden part, and there is no way by which I could link this hidden part to the actual memory location. So, when I go and change the memory location, then it is the duty of the compiler to generate a code which will again move. Once I change that, it will again come and move the corresponding selector inside, so that we start executing. So, this is very important. Okay. Now, there are instructions like LTR and STR, which load task register will store the load the visible part that is given by the programmer, and the invisible portion which is given by the TSS descriptor, right. Similarly, STR will store the visible portion into some GPR or some general purpose memory or general purpose register or memory. So, both of this are possible here. So, we actually saw about the TSS descriptor. Now, let us now look at this TSS descriptor in great detail. So, a TSS descriptor is pretty simple. It has a base address of 32 bits, as you see in the lower part of the slide. It is between 0 to 32, and then there is a segment limit which is again 20 bits. It is like any other descriptor, and the type is 10B1, that B is available bit, and that is basically I do not care, and then the P, the present bit and the DPL is there, then there is an available, there is a G bit. Okay. So, the B bit is basically the busy flag, whether the task is busy or task is currently running or is suspended. Okay. So, this is basically as far as the user is concerned, it is a do not care, you can fill it with whatever you want. The system will update this B bit accordingly. Now, what we need to get here is, in the TSS descriptor there is already a DPL, right, and very slowly we are trying to build up the security. We have to be extremely careful in understanding this security, because this is the crucial thing about transition, because all vulnerability, if at all that could come, this would come in this type of a transition. Now, there is a DPL here in this TSS descriptor. So, if some other code wants to use this descriptor to do a task switch, that CPL should be less than or equal to this DPL. Okay. So, there is one first level check that is made. So, as an operating system, I can put the TSS descriptor only in the GDT, I cannot put it in the LDT, and once if I put it in the GDT, there also I as an operating system can set a privilege level, so that only some privileged code can access. I could have a control there, and that is very important for us to realize. Now this is the actual task state segment, that is that 104 bytes that we have seen yesterday, and all that we have described here is still here in this diagram on your left hand side, and you have placeholders for all these 6 segment registers. You have a LDT segment selector, that is for every process can have its own LDT. You have a placeholder for all the 8 general purpose registers, EAX to ESI EDI. Then you have EFLAGS, it is which is also the flag at the time of suspension, what would be the suspension of the task, what would be the value of the flags. You have EIP, which is the instruction pointer. Then you have CR3, which is the page directory based register. So, you can have your own page for every task, and then you have SS2, SS1, SS0, which are the segment selectors for the stacks, then ESP2, ESP1, ESP0, which are the stack pointers, and then you have also a link for previous task. If a task A calls task B, then the task A's thing is linked to task B. So, there will be a link from task B to task A, because after you finish executing task B and you do a return, then it has to go back to task A. So, this in operating system terminology, this can be viewed as a process control block or a context of the process, and this is essentially necessary for me to restart the process. After once it is suspended, I have to get back. Where it will restart, please note that the 32 byte here is EIP, and it will restart at that instruction pointer, the address stored at that EIP. Okay. So, this is how a task state segment is conceived of. and you see that there are lot of black or grey areas, and those things are undefined and they are reserved. So, you can put any don't care value when you are building this task state segment. Now, let us take a very quick view here, that when the operating system wants to execute a task, you always see in the textbooks that you create a task. What it means to create a task? To create a task, which we are going to do as a part of the assignment, to create a task, what we do? We create the data segment, the stack segment, code segment, their LDT, their page table if necessary. Then we initialize all the registers, then we initialize EFLAGS. We load the program. Say now we loaded in the previous session, we loaded the program in A1000. So, we also load the program somewhere, and that starting point you store in the TIP, then create stacks for the different privilege levels, put everything, and now go and task switch into this TSS. This is what we mean by operating system creating a process. So, the operating system creates the TSS, fills it with correct entries, and then it transfers control to the task state segment. It jumps into the task state segment, or it calls the task state segment, so that it starts executing, and when the task returns, it will come back to the operating system. You got this? So, this is what we mean by creating a task from a operating system perspective. And what things can go wrong here? For example, if your CS code selector has privilege 2, your SS should also have privilege 2. So, things like that can go on. For example, if your CS has privilege 1 but your SS has privilege 0, or your DS has privilege 0, then it will not allow to hold. So, when the task switch is happening, the architecture checks all these things before it allows the task switch. Right? For every segment selector, it will go and check if so first it will load the code segment, right. So, then now the current privilege level is set. Based on that, it will check for all the other segments whether certain segments can go or not. So, there is lot of architectural level checks that happens before you do a task switching. So, even if the operating system makes a mistake, if you fix the code segment correctly, all the other things will essentially be the privileges, at least at the privilege level, all those checks will be done by the architecture, right. We are going to describe those steps in a very quick way as we progress in this lecture, but please note that this check essentially adds lot more confidence to task switching, and if we call that, this is one of the most important architectural aid for security. So, the TSS descriptor is a segment So, there is also some small things like there is a T bit at the 100th byte. If this T bit is set, then it will raise debug exception when task switch occurs from the task, right. So, when I move from this task to another task and this T bit is set to 1, then it will raise the debug exception. Debug exception is exception number 2 or 3, one of those. So, it will automatically go to the service. So, whenever the task is switching, I know that it is switching, right. So, this is another small feature that is available as a part of task state segment. Now, the other way of accessing or going to another task is through a task gate, through a TSS descriptor, to a TSS. The first method was directly to the TSS descriptor to the task segment, to the task state segment. The second method is I go through a task gate to a TSS descriptor to the task segment. So, why do you need this? Can anybody tell me why do you need this? So I can do it at the TSS descriptor level. If you say it can, I can make it more secure, then I can make it happen in the TSS descriptor stage itself.
But in this, it will always have a track of which process is accessing that.
Right? No, the reason is that the task gate is like a call gate, right. So please note that if I want, so let us take this scenario. I have 3 privilege level 3 codes, A, B and C, right. I want A alone to jump to some task, B and C should not jump to that task. If I want to permit A to jump to that task using only the TSS descriptor, what will happen? I have to put the TSS descriptor where? In the, I can only put TSS descriptor in the GDT, and in the GDT I have to create a privilege level 3. Now if I create privilege level 3 there, then all these fellows can access that. But I want only A to access, not B and C. So what I do? I make it privilege level 0, I put another gate here which points to that, right, and that gate I make it privilege level 3. So I can go through that gate, through this task gate, through the TSS descriptor, and then basically go and do the task switch. And this gate, right, this gate I can put it in the LDT. So I will put the, so for process A alone I will put a task gate in its LDT which will point to the task stage segment descriptor in the GDT, and it can go there, and for the, but the task stage segment descriptor will have privilege 0. So I will go only through the task gate, while for the other two I will not put the task gate there in their LDTs. So they cannot access, but I can still access, right. So there is something like many point of time you will have certain objects which you want only certain people of a privilege level to use. I do not want everybody in a particular privilege level to use me. I want to classify that subset of people who need to come and use me, correct. I do not want every privilege level 3 to come and use me, but I want one fellow to use me, correct. And to achieve this I use the notion of this task gate, right. So I make myself PL0, so no PL3 fellow can jump to me, but for one fellow who wants to access me, for that person alone I will give a task gate in its LDT so that he can use that to access me, but other fellows cannot access. So this is very important, okay. So the structure of the task gate is, there is a TSS segment selector here, there is a present bit DPL 0, 0, 1, 0, 1, this is 5, this is the type, and this is a system descriptor, so it is 0 percent DPL, and I just have a TSS segment selector. So a task gate descriptor is very simple to see. So the thing is, my CPL or RPL of the calling task gate selector should be less than or equal to the DPL of the task gate. So when I am calling that task gate, right, I say I jump to that task gate, my CPL should be less than or equal to DPL of task gate. If that is done, that is enough, then there is no more check, right. So this is how this works. So this is the LDT, IDT, so the task gates can be in LDT and IDTs, For example, IDT also, yesterday I told there are instances where I cannot use an interrupt gate or a trap gate, I need to use a task gate. Actually I need to do a context switch for solving certain interrupt related routines. Why should I do that? We took the case of the double fault, right. A privilege level 0 code creating a double fault, creating a stack fault, having a stack fault, right, and it tries to push more things into the stack, and that creates a double fault. In one of the sessions I also clearly explained the difference between a double fault and a fault got when executing an interrupt service routine, right. So that is these are some things that we need to very carefully understand, right. Now, so the IDT will also have a task gate, your LDT will also have a task gate, and this task gate will go to a TSS descriptor. Your GDT can also have a task gate, and then it can go to a TSS descriptor, and this is the TSS. And note that there is a nested flag NT flag in the EFLAGS register. This is the 14th flag of the EFLAG register. So what will happen is, there is, if I am going to do a task switch, for example there is a caller task which is going to call another TSS descriptor through a call instruction, or it can come through an interrupt or exception. The moment I call a task state segment selector or a task gate, either through interrupt or through normal calls, right, or any exceptions, right, immediately I go and set the NT flag. What do you mean by NT flag? NT flag for the called task. Essentially that means that if my task finishes, there is somebody else that I need to transfer control. It is not that it's completely over, because this task switch has happened because of a call. So when I finish, then I have to return back to the caller. I need to get that captured. So this NT flag is basically done. So the IRET actually modifies this flag on return from the call task. So caller task calls the call task, and the call task finishes its work, and it comes back to the caller task. While it is coming back, it will reset the NT flag, because there is no more nesting. I called you, so there was a nesting. When I come back, I lose the nesting. Okay. So what are the types of task switching? So there is a caller task and there is a called task. So jump or call instruction to TSS descriptor in GDT is one way of task switching. Jump or call instruction to task gate descriptor in GDT or LDT, this is another way of task switching. There can be an interrupt or exception vector in the IDT, in your interrupt descriptor table. I have something called the interrupt gate, I have something called the task gate. Now I have a trap gate or a task gate. If it is going to be a task gate, then there is a task switching. So because of these three instances, I could have a task switch between a caller task and a called task. From the call task to the caller task, you basically go back using an IRET instruction. So IRET instruction will take you from the call task back to the caller task when NT flag is set, right. The nested task flag should be set, because NT flag essentially says that somebody has called you, so we go back to this. So what are the stages in this task switching? So I am repeating, it's quite, I have been covering this again for, this is the third time I am covering this, but every time I am slowly going into depth, because the first time I teach you the complete depth, it actually drives you mad. So let me slowly go into a little more depth into what happens when we want to do a task switch. First I say call some segment selector colon dummy, because that segment selector can be a pointer to a task gate, or it can be a pointer to a task state segment descriptor. So get the segment selector from call / jump. For example, if I say jump 0x79:0, this is essentially means the TSS segment selector 79, sorry, it is not 78, 79. So, for IRET instruction, from the previous task link field of TCS you get this. So, if I do an IRET, it is also returned from the task, it is also a task switch. So, what happens? I am returning from a particular task to another task. So, I have a link, as I told you in the previous slides, there is a previous task link that you see on your left hand side. So, I use that previous task link to go to the previous task state segment, and there I get the I reset the NT flag, and I actually get the field of TSS from the previous task link. So, this is how I do a IRET. So, then after doing this, I go and check the privilege. Now, I am going to go from something. So, now let me say that I am going to go to 0x79. Now, what is the 0x79? It can be a TSS descriptor or it can be a task gate, then only the task switch is going to happen. So, if it is a TSS descriptor, go and see if the current privilege level of the caller task, that is the fellow who has executed jump 0x79, and RPL of the segment selector, the 0x79 will have a request privilege level, the max of that, is it less than or equal to the DPL of the TSS descriptor. If it is less than or equal to the DPL of the TSS descriptor, okay, now we can go ahead and do the change. Okay. Now, on the other hand, if we say, if you want to go through a task gate, again you do the same thing. You compare the CPL of the caller task and RPL of the segment selector of called task is less than or equal to DPL of task gate being referred. So, what do you mean by RPL? I say no, jump 0x79, that has an RPL. The 0x79 is a task state segment descriptor of or a task gate of the called task, right. So, if that max of RPL comma CPL it is less than or equal to DPL, then I permit. So, this is one privilege that I make here. And please note that privilege level does not inherit from caller or call to task. Each task separate privilege level is maintained in hardware, right. I cannot say I am of the privilege. So, a task of privilege level 3 calls another task, it is not, that also becomes privilege 3 unless it is a confirming code segment, right. So, every task has its own privilege level and we maintain it. Now, I go and check other information. For example, is the TSS, is it present in the memory? So, there is a present bit for the TSS descriptor, I go and set it is present. Then if it is present, then if the caller task TSS, called task TSS and all segment descriptors used in the task switch are paged into system memory, okay, right. Why? Because my caller task TSS should be now gone into memory, my call task TSS should be loaded from the memory into the registers, and all segment descriptors used in the task switch are all paged into system memory. Now, after doing this, what is happening here? The setup flags, we have to set up flags for caller task. So, the busy flag B in the DSS descriptor is set to 1 if it is initiated by call, and if it is initiated by jump or IRET, it is set to 0. For example, I am a caller routine, I call somebody, that means till he finishes I cannot execute, so I am busy, correct. But if I am just jumping to somebody, I am no more busy, because I have gone there and he may come back or not, so I am not busy. But if I call somebody till he finishes, I am still busy. So, that is the notion of, if I initiate by busy, we initiated it by jump or IRET, then the busy bit is 0, but if I am initiating it by a call, then the busy bit is 1. Similarly, nested task, if it is initiated by IRET, that means a return, that means the nesting is over, NT is 0. If it is initiated by a call /jump, your nested task can become then what we do is we save the context of the caller task. So, we obtain the base address of caller TSS descriptor from TR and copy all the task state information into the TSS, because TR will point to the selector with base, limit, etc. of where the TSS is stored. So, through task register I can find out where the TSS is stored. So, you go and load everything into the TSS descriptor. All caller task data is loaded into the TSS, into its TSS descriptor. Then for the called task, if it is initiated by a call or jump or iret, I become B equal to 1, because now I start executing. I am the called task. I may be the interrupt service routine, or I can be another switch task. But and nested task in EFLAGS, if it is initiated by iret and jump, then NT is equal to NT flag value from called task TSS. If it is initiated by call, then NT equal to 1, right. So, if I am initiated by jump, then my what is the NT? It is the NT flag of my fellow who is jumping into me. If I am initiated by a call, my NT is 1. If I am initiated by my jump, why should I be the NT flag of, why my NT flag should be the NT flag of who jumped to me? Because please note that there might be a call to a routine and he may jump and that fellow may also jump, and somewhere I will go and return my call. Followed? So, there can be a jump inside a routine, but somewhere I will go and return it back. So, when a particular caller jump into a particular another caller, which is another called task, the NT of the called task should be equal to the NT of the caller task, because it can be part of some basic call, but I am doing intermediate jumps, but there is still a call there. Okay. So, this is also very important. Now, I load the context of the called task from TSS. First, as I wrote the TR to point to the new segment selector. The TR old segment is over, now new segment selector. I load the task and information from that new segment selector into the corresponding registers, etc., and load and qualify all the segments. Importantly, I qualify all the segments, right, because if I am a privilege level 3 code, current privilege, my code segment is privilege 2 and my data segment is privilege 0, then I do not allow loading it, right, because if I am a privilege level 3, I can only access privilege 3. If I am PL2, I can only access PL2 and 3. So, if my code segment has a privilege in the task stage segment, if my code segment has privilege 1, it will not allow me to load a PL0 as a data segment. After task switch, the called task will start resuming if there is no error so far, otherwise it will create an error or exception if depending upon what the issue is. So, this is how, so there could be a top level task which was calling another task, which called another task, which called another task. So, that current task register will actually point to the previous task link, which are essentially points to a previous task link, and like this. So, I will have, when I do a nested of calls, I actually create several TSS in a list. So, in the operating system terminology, there is a process control block, right, there is something called a process control block, which, and these process control blocks are all part of a list, and they can be in the ready list, or they can be in the wait list, or they can be in the suspended list, right. So, how do you form such list? This is how such type of list can be formed using hardware. Many of the OS does not use it, but still you can use it.